Happy to see so many people here today. And today we have the great pleasure to have here YOSHUA BENGIO. As you probably know, YOSHUA is one of the pioneers of deep learning. YOSHUA is a professor at the Université de Montréal. He's also founder and scientific director of AMILA, which is the largest academic lab working on deep learning. YOSHUA received many awards in his career, and very recently the Turing Award, which is considered the Nobel Prize for computing. So it's really a great pleasure to have YOSHUA here, giving a keynote on deep representation learning. Thank you.
So please don't hesitate to interrupt me in the middle of this lecture to ask questions, and then we'll also have a question period at the end. So the starting point of deep learning was actually the idea that we could learn powerful representations that would capture the underlying explanations and factors behind the data in a way that would not require humans to specify the meaning of those factors. In standard supervised learning, we tell the machine what the important high-level concepts are by, telling the labels and so on. But often we'd like machines to discover high-level concepts. Even in supervised learning, we may have intermediate concepts that we don't know about in a formal way, but would like machines to discover. And then, of course, in many cases, we have unlabeled data and would like computers to make sense of observations from the world or interacting with the world. And one of the ideas that I proposed more than a decade ago is the idea of disentangling those explanatory factors, to separate them. It's like they're in the data, but they're hidden because they're intertwined with each other, and it's hard to separate them. And if we can separate them, it would make further machine learning tasks easier, because most of those tasks would only require access to a few of those factors, and they would be almost like evident in the representation. That's the goal. It's related to the older idea in pattern recognition, computer vision, speech recognition of invariance. The idea of invariance being that we'd like to build features or representations that are sensitive to the aspects of the data we care about and insensitive to the other aspects. But when you're doing unsupervised learning, well, you don't know what the task is going to be necessarily, and so you don't want to throw away information that might be important. So in speech, let's say you have unlabeled data and you want to discover a good representation. Maybe this is going to be used for speech recognition, in which case you don't care about speaker identity. But if you're doing speaker identification, you don't care about the phonemes, right? And since you might not know ahead of time which of the tasks will come in the future, you'd like to learn representations which don't throw away any of these important factors, but somehow separate them from each other so that it'll be easier for, say, a classifier to distinguish the factors of interest. So we talked about it for a few years, and then in 2011, we actually started doing experiments where we just observed that without any special terms in the objective function, simple unsupervised representation learning methods in those days based on denoising autoencoders were able to discover representations in which some of the dimensions seemed to focus on factors we knew were relevant, and then other dimensions were focusing on other factors. So unfortunately, if you think a little bit deeper about this problem of discovering good representations and disentangling, there is a sort of non-uniqueness problem, that there may be many solutions to finding good representations. For example, if I have a good representation, I could do any invertible nonlinear transformation of it, and it would still be a good representation from the point of view of producing the low-level data. So in order to be able to separate the interesting features, we need extra clues, if you want, maybe in the architecture or in the objective function, to encourage the kind of separation that I've been talking about. And over the years, people have been proposing many kinds of clues. The one that people are focusing on these days, and I think is sort of overrated, is the idea that the high-level factors should be statistically independent. So that's what's called marginal independence, meaning if I look at the joint distribution of the hidden layer at the top, say, this joint distribution could be approximately equal to the product of the marginal distribution, so the variables are independent. There was, in the last couple of years, there's been a number of NeurIPS workshops where people go for that objective, but I think it's exaggerated constraint. And in general, if you think about high-level concepts that humans think about to explain data, things like the words we use in English or in French or whatever, they tend to be not statistically independent, right? But they have sort of simple structure that make it easy to represent their joint distribution nonetheless. There are other aspects which I won't have time to talk about very much, like the relationship between those factors and what humans would consider causes and effects, which explain what we see in the data. And that's related to the notion of agents. So it's a little bit far from what you think about in speech, but when you think about AI and agents in the world that are interacting with their environment, things like this object I can move around and I can control separately and independently from other objects. And that makes it an interesting aspect of the world, which I would like to represent explicitly in my high-level representations. One aspect that people have been using, and I think is very relevant to speech, is the idea that different factors are associated with different spatial or temporal scales. Right? So you can clearly see in speech that there are phenomena that explain the raw data that happen either at a very slow scale, like say slow linguistic processes, or the emotions that we're trying to express in the speech. And then there are things that are happening very, very quickly at the level of tens or hundreds of milliseconds that are kind of low level in nature. And you can, there's no space in speech, but you have frequencies, and you may also imagine that there are things happening on a frequency scale that are interesting to consider. There is a geometric point of view which I really like, and I've been promoting for a long time, which helps understand from a different perspective what we want from these high-level representations. And the idea originates in earlier thinking in machine learning about what's called manifold learning. So it starts from what's called the manifold hypothesis. The manifold hypothesis states that most of the probability mass is concentrated in a small region that actually is near a lower dimensional set of points, a manifold. So one way to convince you of this is imagine you were to generate an acoustic signal in a completely random IID way, where you take each acoustic sample independently of all the others. What you would get is some kind of white noise. And now you can ask yourself, what's the probability that by this process I would produce something that sounds like speech? Well, you would say 0, right? Or very, very small, exponentially small. So what does it mean? It means that the set of acoustic sequences that correspond to speech occupies a very small volume in the space of all possible sequences. So that's the manifold hypothesis. And it's true for images, it's true for speech, it's true for text, it's true for most interesting signals or data that AI is involved with. Okay, but why do we care about this concentration of probability? Because not only the probability is concentrated, but it's concentrated in a region that's not flat, in a region that is curved. And you can also come up with arguments to show why it's highly curved. And you can do experiments that we've done to see, it's like a spaghetti. So that's what I'm trying to express with this picture. The data is concentrated on a sort of high-dimensional spaghetti. And that makes it very hard for statistical methods and machine learning to capture the distribution of the data. If you imagine trying to cover that spaghetti with a lot of little Gaussians, well, that's what traditional HMMs with Gaussian mixtures were trying to do. And you need a lot of data, and you need a lot of little Gaussians to cover all of the ups and downs of these spaghettis. So if we could take the raw data and just transform the space nonlinearly so that the spaghetti becomes flat, that would be great, because then it would be much easier to capture the joint distribution of the data and probably answer all kinds of interesting questions about it. So that's one perspective. And when you think about it this way, it's natural to think about two functions, one that maps the spaghetti to a flat one, that we call the encoder, and one that goes in the other direction, which we call a decoder or a generator. In particular, if you wanted to generate things like speech, then once we have flattened the spaghetti, it's like something we can model with a Gaussian or a very simple distribution. So if we wanted to generate a point on the spaghetti, we could just generate from that high-level simple distribution, like a Gaussian, that's concentrated where the flattened spaghetti is, and then we could apply our decoder or generator function, and we would get a point on the curved spaghetti, right, in the data space. And in a way, that's what things like GANs and other deep generative models are trying to do. So there are other reasons why thinking about high-level representations and a latent space could be interesting. The hope is that some of the dimensions or directions in space in the high-level representation would correspond to meaningful attributes. So say for images of faces, maybe there will be directions that capture gender, directions that capture age. And because the space has been flattened, it means that the distribution in the high-level representation now is more or less occupying a convex set. So the property of a convex set is that if I take 2 points on it, I can interpolate between them, and the points in the interpolation are still part of the set. And so what you can do things like, to verify that this works, you can do things like take 2 images, or you could do it with speech, but it's easier with images, map them to the high-level space, and then interpolate linearly between those points. And then for each intermediate point, you could use the decoder to map back to the data space. And here you could visualize the points in between as images. Now, if the learning had not worked and the high-level manifold was not flat, then what we would see in between would not be things like natural images of faces. Think about, if we go back to the spaghetti, if I take 2 points, say like this one, and I draw a line in between, the images that I'm going to generate in between will not be part of the data manifold, and so they will not look like natural images. But when I flatten it and I take like a point here and a point here and I interpolate, it kind of works well. The things in between do belong to the data manifold when projected back in the data space. So we can do these experiments. People have been doing these things for years now, and it's a way to validate that we have discovered a flatter representation of the distribution. And it also can be used, I mean, imagine doing computer graphics, or here we can transform a male into a female, and fun things like this. And of course, as I said, you can use this encoder and decoder to infer high-level representations or to generate low-level things from nothing, from sampling from the high-level distribution. You can also do semi-supervised learning because, again, this is a hypothesis, but if we have done a good job of disentangling the underlying factors, then questions like separating here between males and females become much easier in that flat space. Very often, you're able to actually answer all kinds of questions with a linear classifier. And people have done a lot of experiments with unsupervised representation learning, showing that indeed linear classifiers can perform fairly well on the top-level representation compared to doing it on lower layers or on the raw data. And so you can then take advantage of this either in a simple scenario where you pre-train with unsupervised unlabeled data and then you train the classifier, or you combine the supervised and unsupervised objectives where you have both labeled and unlabeled data. Okay, let me now go back to a little bit of basics about some of those methods, in particular the GANs, generative adversarial networks, and how we got to this. So a lot of machine learning methods are based on maximum likelihood, but maximum likelihood has some issues when the data distribution is concentrated on those manifolds that I've been talking about. Imagine, for example, that we have a data manifold that's curved and complicated, but the probability is concentrated, and somehow we build a model that also concentrates probability, but not exactly in the right place, but very close to it, like in the picture. Well, according to maximum likelihood, the training objective for this would be terrible. And so instead, what maximum likelihood would lead to are models which spread out the density to make sure that every point in the training data and the validation set will be covered by the model. And so you get models that will then generate, if you sample from them, things that don't look at all like the data, right? And so one idea that has been explored in the literature, in particular, we were a lot inspired by the work of Uvarinen in Finland, is the idea that maybe we can use the technology of classifiers in order to build models of the distribution. And you can see how a classifier could be used for this in principle. So imagine that you have this data manifold again, and now you train a classifier where the decision surface is, say, this dotted line, dotted curve, which separates the inside from the outside, which separates the high probability samples from the low probability samples. And in fact, if this classifier is a probabilistic classifier, then the score that you get out of it would be, say, high where you're close to the data manifold and low if you're far from it. So this idea, there's been many variations on that theme, and we've tried a bunch of things which didn't work. Until we stumbled onto a game theoretical scenario called GANs, which worked really well, at least for images. So the way that this game is going to be played is we have two networks. The network that we care about at the end is representing the distribution through a generative process rather than through a density function. So a lot of the classical work in machine learning and statistics, including in speech, involves representing the distribution of the data through a formula that computes the probability of the data, a density function, because if you do maximum likelihood, you need that. You're going to be computing the derivative of those probabilities. But that's one way to do it, and it's tied strongly to the maximum likelihood framework. Another way to represent a distribution, which is particularly convenient if what you want to do with the distribution is to sample from it, like in speech synthesis, is to train a generator. In other words, a machine that's like taking random numbers and outputting things that are coming from the distribution you're trying to model. So that's what the generator network in GANs is. You throw in, say, a Gaussian vector, and it's trained to transform the the Gaussian vector into something like the distribution. And remember, this is exactly the scheme that I told you about here, right? We start from a very simple distribution, which is, say, Gaussian, and we're looking for a generator which transforms nonlinearly the space so that this Gaussian becomes a spaghetti. And not any spaghetti, of course. The right one. Okay, so how do we, the problem with generators is, what's the objective function? Like, well, if we don't do maximum likelihood, what is it we'd like this thing to do? We don't have a target for this. But what we can do is bring in a second network, which we call a discriminator network, which will compare, which will be able to say whether an input comes from the generator or comes from the data distribution. So it's comparing two distributions. And in a way, it's similar to the classifier I was telling you about, inside and outside, but it's slightly different. Now it's the data distribution versus the model distribution, the one that we're learning. And it's trying to find a way to recognize that the generated thing isn't quite right, isn't quite like the real data. And if it finds features that can do that, that means the generator isn't doing quite the right job. But we can turn this upside down and say, well, now we can train the generator so that it fools the discriminator. In other words, the discriminator becomes an objective function, a loss function. So this is a new idea in machine learning. Traditional machine learning, somebody gives us a loss function. Here, it's like we're learning a loss function. Right? So this is a very powerful idea. Of course, it also came with all kinds of complications because we don't have one objective anymore. We have two networks, each with their own objective, and we enter this sort of really unusual game theoretical scenario. In the simple version of the objective function for the GANs, we can think of it like a game where we have one objective where one of the network is trying to maximize the objective and the other is trying to minimize it. It's a saddle point problem. Okay. Now, let me shift gears towards some recent applications of some of the ideas with GANs in order to capture a notion of dependence between random variables. So remember I told you about one of the objectives that people are looking for in disentangling is to try to make the variables independent. Well, independent variables have this property that their joint distribution is equal to the product of the marginals. So for example, for two variables A and B, P of A, B is equal to P of A times P of B. So how is that interesting? Well, you can take samples from the joint distribution and you can shuffle the features, the dimensions, so that you get samples from the product of the marginal. So for example, if to get a sample from the marginal, I can pick a one random example and I take the dimension A, and I take another random example and I take the dimension B, and I can do that for every dimension. And now what I have is a sample that has the right marginals, but the joint is completely broken and the variables are independent. So from samples from a data set of or like a mini batch coming from the joint, I can construct another data set which comes from the product of the marginals. So now I have two distributions. One which is the real data, whatever this was produced, and one which is a version of it where we've made the variables independent. Okay, so what I can do is I can train a discriminator, just like in GANs, a classifier, that's going to tell apart a particular tuple of variables and tell me if it looks like this is coming from the joint or is it coming from the product of the marginals. In other words, it's going to tell me, do they look independent or they're coming from the joint? And if you want to make those variables independent, for example, if the joint is coming from a a neural net that takes raw data and transforms the data into a space where we would like the dimensions to be independent, then we can use this discriminator as an objective function to encourage this guy to produce samples that look like they are independent. So that's one idea which is connected to notions of mutual information and entropy. And a follow-up on this came last year, ICML in 2018, the work that was led by Belghazi at Mila, where we essentially follow the same kind of architecture, but we modified slightly the objective of the classifier so as to guarantee actually that the classifier is producing a score whose average is an estimator of mutual information between the variables. Right. So this little equation here, for those who know about mutual information, this is just a definition of mutual information. It's an expectation over the joint of the log of the joint density divided by the product of the marginal densities, right? So the same objects I've been talking about. And so in a way, you can think of this as a score that compares the two hypotheses there. You know, it looks like the joint or it looks like the product of independent variables. And so it turns out that with the proper objective function for the discriminator, we can get an estimator for the mutual information. And now we can use this. Before I use it, so again, let me use a similar trick. Let's say you want to train an encoder where we maximize mutual information between the input of the encoder, which might be an image, say, and a learned representation y here. So one way we could do this using these kinds of ideas is we can generate two kinds of data points. When the x and the y are coming from their natural joint distribution, where y is the output of an encoder that takes x as input, or when x and y have nothing to do with each other. So for example, we take an image and we take an output of the encoder for another image, and so you know they have nothing to do with each other, but their marginal distribution is correct. So we have these two distributions that I told you about, the distribution of the joint and distribution of the product of the marginals. And so we can produce samples of both of these distributions. And now we can train a classifier that is trying to separate these things. And then the score of the classifier, which in a way measures how far you are from the decision surface, using the math I told you before, will measure mutual information between the input and the output of the encoder. So it's also interesting to note that mutual information is connected to entropy, and there's this particular identity here that says the mutual information between two random variable x and z is the entropy of one minus the conditional entropy of that one given the other. So in the case where the variables would be discrete, which is not our case, but in the case where they would be discrete and x is a deterministic function of z, the entropy of x given z is 0. And so maximizing the mutual information between the input and the output of some neural net is equivalent to maximizing the entropy on the output of the neural net. So one way to think about this is for the output of a neural net to have maximal mutual information with its input means that we don't throw away any information about the input. We maximize the entropy of the output, and it's all equivalent. So this has been used to improve, to deal with one of the problems with GANs. So one of the problems with GANs in their standard formulation is that they tend to generate nice-looking images, but they miss some of the modes of the distribution. So what it means is they get the images that they're generating looks nice, but it's like there are images that they will never generate, but still should be part of the distribution, right? So let's say this is our data in this toy problem, and maybe the GAN is going to generate samples from this part, but somehow ignores this part. If we add a regularizer kind of penalty on the output of the generator to maximize its entropy or maximize its mutual information between its inputs and its outputs, then we get a generator that does a better job of covering the whole distribution. We can play the same game with these other toy data. So let's say the distribution is a mixture of Gaussians in 2D like this. So these are like this is the density, and a regular GAN might get some of these modes, but miss a whole lot of others. And then if we add this regularizer, we recover all the modes. And we've done a bunch of other tests to verify when we know what the modes are, that these kind of regularization manages to recover all the modes. So one way to do that here with MNIST images is, well, we know that MNIST digit images have 10 modes, one for each of the 10 digits. So now if we take 3 digit images and stack them on top of each other, let's say one is red, the other is green, the other is blue. So we get one a 3D image, 3-channel image, and we take that as input data. We know that the number of modes is going to be 10 by 10 by 10, right? So there's 1,000 modes. And because they're images, it's very easy to detect those modes because we can just stick in a very good classifier and it will tell us whether the red looks like a 1 or 2 or 3 and so on. And so we can identify, oh, in this image, it's the mode corresponding to red is 1 and blue is 6 and green is 5. All right, so we can then verify that the samples we're producing cover what fraction of the modes. And we can then compare different methods for how well they recover all the modes. Okay, now there is some interesting thoughts that we've been exploring in the last couple of years about these ideas of learning representations where the goal is not to generate, like in GANs, but to produce representations and to produce these latent features that don't necessarily capture everything in the data, but somehow capture interesting things. So how is that interesting? This is connected to a larger area of research in machine learning that my friend Yann Lequin is pushing a lot, called self-supervised learning. So the idea is that in any signal, you can do unsupervised learning without doing maximum likelihood by just asking some parts of the data to be predictable from other parts of the data. And then which parts is which is a question that may vary. For example, you take that sequence, and that's the video, and then you ask the question, what was the order? Right? You can present that sequence left to right or right to left, and then ask a classifier, what was the original order? And you can see that if you're able to answer that question, you're capturing something fairly high level about the semantics of images that capture the physics and other aspects of, like here, horses running. Another example is you take patches in images and you ask whether they come from the same picture. Or you take different patches and you remove a patch and you ask where does it belong among other patches that are missing. Or you take a sentence and you ask what would be the next sentence, or what would be the sentence before. Or you remove a word in a sentence and you ask, what was that word? All right, so there are many questions like this that people have been looking at, which give rise to representation learning as a side effect. So instead of asking those questions directly in the data space, these tools that I've been telling you about with mutual information can be used to learn representations and to ask those questions about mutual predictability, predict one thing given another thing, not in the data space, but in some latent space. And that's really cool, right? Because often, so think about speech, right? You don't want to predict acoustic samples from other acoustic samples. I mean, that's what autoregressive models do, like RNNs. But really, the thing that makes more sense intuitively is would like to predict high-level things like the next phoneme given other high-level things. Well, for phonemes, we can do it because, well, we have the labels, but there may be other high-level variables that we don't have labels for and would like those things, those algorithms to discover those features, and those features should have the property that they are mutually predictable from each other and capture information about the data. Right, so we can do that. We can say, take two patches in an image, map them to a representation space using the same mapping that you're going to be learning, and then ask that there's high mutual information between the representations. Right, so now we are able to do that because we're doing something like maximizing mutual information. If we were just trying to do prediction, like maximum likelihood prediction, so let's say predict this guy given this guy or vice versa, what may happen is that it would learn an encoder that can collapse to a constant function. So why is that? So if I was just trying to predict this given this, the optimal answer from the point of view of the objective would be to learn a function that outputs always the same thing. Because if the output is always the same thing, it's very easy to predict, right? But that's not what we want. What we want is that this is predictable from this and vice versa, and that this preserves a lot of information from this. If it's constant, of course, we throw away all of the information. Okay, so that's what these tools allow you to do. Yeah. And in addition, in more recent work was presented at the last iClear conference, what we've been exploring is the idea that we can apply these mutual predictivity, mutual information objectives, not just at the level of like patches or segments, but we can do it at multiple scales. Because there might be features, as I told you before when I was talking about different scales in speech, there might be features that belong to different scales, different temporal scales, different spatial scales. All right, so how are we going to do that? So first of all, let's see if we try to maximize mutual information between patches and a global feature vector, what's going to happen? Right. So now, instead of comparing two patches together, we're going to compare one patch with a global feature vector that's extracted from the whole signal. Right. So now we're saying we'd like to extract local things that are predictive of global things that cover a larger scale, right? So the short-term things should be related to the long-term things. Of course, the short-term things should be related to each other as well. So what happens is, in a say a picture of a cat like this, there are a lot of patches which implicitly contain information about the underlying high-level object cat. And so when we maximize mutual information between the low-level patches and a single global feature vector, which is obtained from the whole image, the dominant categories, if you want, will pop out in both the local feature detector and the global feature detector. So then there's a question that's not easy when you do unsupervised representation learning, and that is, well, how do we know that it's doing a good job? Because we're doing this unsupervised stuff, and we get feature vectors. Maybe local feature detectors or global feature detectors or different scales of detectors. How do we know that they're doing a good job? It's actually not an easy question. Now, when you write a paper, you have to try to answer it, because otherwise, if it's just qualitative results, reviewers tend to not like it. With reason, because we'd like to be able to compare different methods. So even if the techniques we're using to compare are not perfect, we should strive to find ones. So what are the most common ways of answering this? So maybe the most common way, and it's very easy to understand, is to say, well, if we had good features, we should be able to use those features as input to some kind of classifier that predicts factors we know matter. So let's say we are doing unsupervised learning on images, and images that are ImageNet, so they contain objects of different kinds. Then we would like the features we discover to be predictive of the object categories that we have in the labels, right? So we can train the representations in an unsupervised way, and then we can check whether those features, say even with a linear classifier, do a good job of predicting those labels. And we can have different kind of labels that we might want to predict, and we could check how well we're doing this. So that's one way, and we can do it both at the level of the global features as well as the local features. We can, of course, measure the objective function that we're caring about. Here, say, mutual information. We can measure different quantities of dependence. We can also see whether those features preserve information about the original data by training a decoder that goes back from the latent space to the data space and then measuring some sort of reconstruction error. So it turns out that this approach of local and global features has worked really well in terms of predicting image categories compared to existing unsupervised representation methods. And what's interesting is it's getting close, or even potentially sometimes surpassing, the classification error you get with a fully supervised method. So this is, for many years, since about 15 years, we've been fighting with a very difficult challenge, which is, can we do unsupervised learning of representations that can be as good or comparable, or potentially even better, than the kind of representations we get from supervised learning? And usually the answer is no. It's always better with supervised learning. I mean, it's better for that particular supervised task. And I think there's a good reason for this. The reason is, when we do supervised learning with human-provided labels, those labels are not just like random functions of the data. They are the functions that matter in the data, right? Or at least some of the functions that matter about the data. And they contain the high-level concepts that humans care about, that make sense. So they provide a lot of important clues about what's important in data to the learner. And so, for example, if you do supervised learning on ImageNet, and you look at the top hidden layer, so now it's from supervised learning, but you take those features and you use them as input to, with linear classifiers on new categories that are not part of the training data, the original training data, those classifiers perform extremely well. Okay, this is called transfer learning. And it's because the features, the group of features that are good for 1,000 categories of ImageNet are very likely to be also good under different linear combinations to predict many other object categories, right? All right, so the fact that we've been able to reach this kind of performance, at least on these small data sets, is very encouraging, and is a sign that we've made a lot of progress in unsupervised representation learning in the last few years. Related to this, you can apply this technique not just on images, and as Mirko has been doing on speech, but you can apply it on graphs. As maybe some of you know, there's been a flurry of papers in the last few years extending deep learning to any kind of data structure. In other words, instead of working just on vectors and sequences, we can now work on graphs, and these things work quite well. You can play the game of mutual information across in many ways. So for example, as I mentioned, you can do mutual information between different patches in the same image. You can do mutual information between patches corresponding to consecutive images at the same position or nearby positions. And then you can do mutual information between local patches and global patches. And you can do it for the same time step, or you can do it across time steps. So you can see like really all kinds of ways that you can use this tool that we've applied in a recent workshop paper on Atari images. All right, let's see, how much time do I have? Let's say 5 minutes. So now I'm going to look a little bit more forward. Is that good? And tell you a little bit about some of the current limitations that I perceive in deep learning, and especially as it relates to language-related questions, which I think are of interest here. So there's a separation of different types of tasks that humans perform, which has been proposed for many decades by psychologists, Kahneman and collaborators in particular, called System 1, or like the fast system, and System 2 is the slow system. So System 1 tasks are things like what you can do very quickly in half a second, like recognize an image or recognize a sound. And they correspond to intuitive type of tasks, right? So you know it, but you don't necessarily know how you came up with that answer. Whereas System 2 tasks are slow and logical and sequential and conscious and related to language. So if I tell you to add 34 and 21 in your head, you can probably do it, and it's going to take time as you go through the different steps. And when you're done, you could explain how you did it. You can communicate that information to a computer. You can program a computer to do it, right? So when we do programming, we do this all the time. It's a very different kind of processing as sort of the unconscious, non-linguistic, heuristic kind of computation. And deep learning has really unlocked the first kind of computation. But the second kind is the thing that classical AI and, based on logic and symbols, was trying to achieve and hasn't succeeded, and remains kind of open. And a lot of the things that remain in the frontier is, how do we take advantage of the progress we've made on this to unlock this at the same time as this? If we want to make progress in language understanding, I think we need to do that. And what it means is that we should learn about language not just from texts, but also how text is associated with, like, how symbols are grounded in the meaning, what words refer to. So this is called grounded language learning, and then people are doing this using data that combines, say, text as well as images or videos or things like that. In order to sort of highlight this need for grounded language understanding approaches, let me propose the following thought experiment. Imagine yourself going to another planet and observing the aliens exchanging information to each other, speaking to each other. But things on this planet are a little bit different from on Earth, whereas the communication channel that we have with speech on Earth is noisy, and so we have a lot of redundancy in language to deal with this. On this planet, there is, like on Earth, the bandwidth of communication is expensive, so you don't want to use too many bits. But it's a noise-free channel that these aliens have to talk to each other. As a consequence, the optimal communication strategy for these aliens is to compress their message before they send it in the channel, right? So now you know that if we observe a compressed signal, it looks like random bits. So if we're trying to do maximum likelihood on their text, it will just be producing a model that says, well, the bits are independent, there's nothing to say about it. So we can't understand that alien language by only looking at their text. Now, it's not true for Earth natural language. There is redundancy, but maybe it's partially true, and maybe if we only look at text, there will always be some part of the meaning that will remain out of our reach. So that's the message of this thought experiment. And so in this alien world, if we wanted to solve the problem of understanding their language, we would need not just to catch the bits they exchange, but to see the context in which they are acting and communicating to get a sense of the meaning of what they're trying to do. All right. And so this idea that we're getting after the meaning for AI, really what it says is we cannot do natural language processing on one hand and sort of say agent learning, reinforcement learning, and computer vision on the other hand. We need to jointly learn about how the world is organized, how the world works, and how language refers to that. We can't just take text. That's the hypothesis that I'm proposing here. And what it means is, we should not have a separate category for natural language processing. We should somehow integrate it into the larger scopes of many AI endeavors. And in particular, I believe that one of the aspects that machine learning currently doesn't pay enough attention to is how agents, like humans, are able to understand their world by capturing the causal structure in it. And causality is something that we don't capture with standard machine learning, because standard machine learning is about joint distributions or conditional distributions, and unfortunately that's not enough to tell us about what would happen in the world if I did this or if some other agents did that. So that's kind of an open question which remains to be investigated, and very few papers for now, but I think it will grow in the future. All right, I'm going to stop here and put some papers that are relevant to what I talked about. Thank you.
So it's the right time for questions.
We have two microphones, one from there, one from here.
Thank you for your talk. So I wonder whether you can elaborate on the inductive bias of the Informax objective. So why it's a good idea to make your encoder output have high entropy? Would that be lead to less informative? Because this also seems to be doing the opposite of other inductive bias, such as information bottleneck.
Right. No, actually, you want it to be more informative. I mean, high entropy means you don't throw away information. But you have to remember this high entropy objective is one term in a larger objective function. So in the information bottleneck, you're also trying to maximize mutual information, but with something else because you have labels or something. So we're not in this situation. We're in the situation of, say, unsupervised learning. And so really we're trying to answer a different question. This here says, well, we want to maximize information that is preserved, but there's more. So when we start looking at, say, 2 frames in time and maximize mutual information between them, this is very different in nature. We're saying, well, we're looking for high-level features that have the property that they contain information over a long time range, or whatever the time span that we're considering. And they're not only capturing the fast changing stuff, which is probably going to be noise, right? So the thing in speech, for example, or in images that is preserved across many pixels or many acoustic samples, like in the example of the cat image, is a high-level information like there is a cat. Whereas the little image variation on the individual pixel level would be thrown away by an objective like this. So that's the inductive bias.
Okay, there is another question.
The mutual information is really very interesting. I wonder what if I would like to have the directions on the 2 variables to introduce. For example, one variable influences the other one, but not the other way around.
Oh, you mean like the causal relationship?
Yes.
Right. Well, okay, so first of all, if those variables are ordered in time, you know that the future cannot be a cause of the past. So that rules out some possibilities. But actually, the part that I didn't have time to go through is about more recent work where we try to infer the causal direction between two variables using meta-learning. And it would take more time than I have to answer your question. But there is recent work in this direction in machine learning. And it's fairly, say, basic research right now because we are so new to this question of causality. But I think it is going to be more important in the future if we want to build systems that really capture how the world works, and that includes the causal relationship, so the direction of causality.
Another question?
Okay, thank you for the very interesting talk. So I didn't read those papers that you presented, so I apologize if my question seems a bit naive. But I was wondering, why do you need a discriminator to maximize the mutual information? Why not just directly optimize it as a loss function?
Right. Very good question. Thanks for asking it. So, in fact, what you're talking about is the traditional way of estimating mutual information. You build a density model of the joint distribution P of xy, and then you can marginalize P of x and P of y from that model. Now you have three objects, the joint and the two marginal densities, and then you can just compute the integral either analytically or through some integration, approximate integration, and that would be mutual information, okay? Now, the problem is estimating density is difficult in high dimensions, and especially for things like images and sounds and stuff like that. In fact, it basically breaks down. People have been using traditionally things like non-parametric models, kernel methods, statistical kernel density methods for this, and it just doesn't scale beyond a few dimensions. And so one of the things we've done is compare with those traditional methods. So what's going on here is we are not computing explicitly a density. We don't have a formula that we can compute that gives us a density P of xy. Instead, what we have is a score coming from a classifier that tells us, does this look like the joint or does this look like the product of the marginal? So it's a different kind of mathematical object, which turns out to be the one we need in order to estimate the mutual information.
Any other questions?
Questions? I have maybe a related question. So, do you see some space for alternatives to mutual information? Because,
Yes.
Yeah.
So mutual information is one measure of dependency between random variables. And it's one that information theory has studied a lot, and it has lots of nice properties. But in a way, as I guess maybe exemplified by the work we've done with Phil Brakel, the first that I talked about, where we tried to make the variables independent, we didn't get mutual information because the objective function for the classifier was just like a normal objective function. Whereas the later objective with the Belghazi paper and mine uses something a little bit more fancy, which then gives us a guarantee that we're estimating mutual information. But the other guy is also estimating some sort of dependency measure. It's just a different one. And which one is better? Well, I don't think we have theoretical answers to this.
Thank you.
I want to have one question. Thanks for the wonderful talk. So you said that if you have a supervision and unsupervised, and usually the feature that you learn in supervision usually is better, especially
Yes.
if you can transform them to another classes.
Yes.
But imagine those classes are a high-level information. For example, imagine speech. You have one system that trying to focus in phonemes. Then
Yes.
you're trying to do after that understanding on top of it. Will unsupervised be much better because he will keep more information about speech than just focusing in the phoneme, which is local information? So, I'm trying to understand what's the best, what's the compromise with unsupervised to be useful.
Right. So you can think of the potential advantage of these unsupervised representation learning methods as ways to avoid some of the pitfalls that may come from a purely supervised method. So what may happen with a purely supervised method is, say, once it has found features that are good enough to do the classification between phonemes, it stops. I mean, it doesn't need to find other features. And if the task is purely those particular phonemes and no other task, then maybe this is good. Another issue that may happen, I mean, but then of course, if you're interested in potentially other tasks, then having the unsupervised feature learning might compensate and make sure you have a richer feature representation. Another thing that may happen is the supervised learning might find a solution that somehow overfits to this particular task training distribution. So let's say you're doing speech recognition or some speech task, and you've trained on data of a particular language or particular accents or particular recording conditions, but really you're interested in systems that will be more robust to all kinds of conditions. Right? So by being a little bit more agnostic about what are the features that matter, you're more likely to capture something that's more stable across potentially many other related tasks, but different from the one you use for training. So in a sense, you can think of this as a regularizer that can mitigate some of the in-distribution overfitting. So this is a concept that has come up in recent years. You know, in classical machine learning, we think of overfitting in the traditional sense as if you give me data from the same distribution as my training set, I'm not going to do a good job. All right? I have too much capacity, or like I'm specializing too much on the training examples. But there's a new notion of generalization called systematic generalization. A notion of generalization that comes up in meta-learning, where you start thinking not about a single distribution, but multiple distributions. So like I have this distribution I'm training on, but really I care about other distributions. Or maybe I have, say in speech, I have data from many countries, okay? And so you can think of the distribution for each country as being slightly different. So now, really, what you're saying is, I would like generalization across distributions. And so there's a notion of stability and robustness that is different. You'd like to generalize to data that belongs to not the same distribution, but another somehow related distribution. If you have multiple distributions, like in speech, say, different speakers, different countries, different accents, whatever, instead of shuffling your data and sort of ignoring the information that is present in the data about the different nature, the different underlying distributions, you can keep that information, like speaker ID and country or accent or whatever, and then try to build a system that will be robust across these changes so that when you test, you apply your system to a new country, it's more likely that it works. But now it's a more powerful form of generalization. You see, it's generalization across related distributions rather than within the same distribution. This is a very important concept that people are starting to focus on in the last few years in machine learning that really is worth thinking about.
Question? My question is like, because the mutual information, it encoded the information in a different way rather than the other supervised model. So my question is it important for good encoder or a study for encoder structure that makes it work better, like the mutual information?
Well, you know, we're doing research and we don't have a crystal ball, but we do experiments, and these experiments reveal some part of reality. And it looks like we've made progress with these techniques in terms of learning good features. I'm sure we'll find even better methods in the future. I don't think this will be the end of the story. We're just, you know, beginning to see a little bit of how these kinds of unsupervised representation learning could help pure supervised learning, which has dominated the fields of, you know, pattern recognition with deep learning in the last 15 years. But I think it's just the beginning.
So I've got a question about the architecture of the networks.
Yes.
And what your opinion about how important the architecture is. So do you think it's better to have a very generic architecture, or do you see maybe an advantage in encoding some signal processing knowledge in the architecture for example, if you have overlapping speech, you could have like some parameterized separation algorithm inside of your architecture.
Yeah, I do think that playing with the architecture is important. I mean, there's a lot of evidence from the literature in deep learning that many of the advances have come from sort of tinkering with the architecture, and especially if you have an intuition in mind about why a particular architecture would be more relevant to the task. So yeah, it could be that using signal processing ideas in the structure of the computation might be helpful. I gave the example here where at the end of the day, we have this fairly complicated architecture, and you could even have it more complicated where you have many kinds of features at different scales, and they predict each other locally in time and space, across scales and so on. So really there's a lot of exploration of architecture to do. And unfortunately, in current machine learning, and the architecture search problem is a hard one. It's not that we have like a given recipe to find the good architectures. There are methods to search in architecture space in an automated way, but they're very expensive, and they're not really a replacement for using your intuitions about the domain to design those architectures.
Other questions?
In the front.
Oh, okay.
Hello.
Yeah.
Thanks again for the talk. This question is a bit more epistemological.
Okay.
And since you probably have a very high level view on things and how things are going in the machine learning community, some of the things I may say are false, and I've just been told falsehoods, but I invite you to correct me. I've been told that the machine learning community comes up with new ideas and architectures, as you just said.
Yeah.
And then, as it just happens, they sometimes work, sometimes doesn't.
Well, it's not like this. They try many things, and then some work and some don't, and those are the ones which get published.
Yeah. And so... and then I think maybe you come up with some explanations as to why they work, or do you have the idea beforehand, or the intuition? And then I'm seeing some movements in the mathematics community, like they're trying to catch up. Is that true?
Yes.
Do you think that they ever will catch up on and be able to explain why everything that you do work or doesn't, and try to build a more general, more stable framework on how machine learning behaves?
All right, so there were lots of questions there. So let me focus on the theory aspects. So it's true, historically, in the last 30 years or so in machine learning research, that theory has been lagging more intuitively driven experimental and algorithmic development. And those advances in sort of the more intuitively driven algorithmic development are driven both by intuition and by random search, so luck if you want, trying many things and seeing which ones work. But optimization is a way to make this more systematic. So people, as I mentioned, have been using an outer loop optimization in order to search for architectures. So you can make that formal, and you can analyze this and think about the kind of generalization it means. But yeah, to go back to the question about theory, I think there is already a lot of theoretical results which help us understand why the current techniques in deep learning work to some extent. I mean, at a high level, not why this particular architecture, but for example, why does SGD work in the sense of generalizing better, not getting stuck in poor local minima? Why is a deeper network producing better generalization than a shallow one? Why is using distributed representation producing better generalization than other techniques in machine learning which don't enjoy this kind of structure? So there are questions like this to which we have some answers. I think even more theory could be done on these particular subjects. And there's an influx of mathematicians that are coming to the field and trying to understand from many different angles what is going on, what works, what doesn't work. So I think we'll see many more of these theoretical results in the next few years and decades. That being said, I think you have the right intuition maybe when you ask your question that it's very likely that theory and mathematics will not be able to answer all of the questions. Like, in other words, won't be able to predict whether this particular architecture will work on this particular data set before you do the experiment. And there's a fundamental reason for this. The reason is there's a part of the equation that is unknown. So when I say, is this architecture going to work on this distribution? The problem is I don't have a characterization of this distribution. I don't have like a formula for distribution. What I have is just a bunch of samples. And so we cannot predict how well a particular architecture or algorithm or whatever will work on this ab initio, if you want. The only way you can get answers is in an empirical way, by saying, okay, let's try it, and if it works, then we can get bounds that tell me, well, if I have more samples from the same distribution, it's gonna also work. So that kind of thing we can say. But before you get any data, and like before you actually do compute things with that data, it's impossible to know whether any machine learning method will work. Now, in practice, we are able to answer these questions because maybe we've played with other similar data sets, or we've played with a particular sample from that same distribution and then we saw that it worked, and so on. And so we are able to answer these questions. But like from tabula rasa, it's impossible to answer the question about generalization for a specific choice of algorithm and architecture and a specific distribution that is not given to me except in the empirical form of a bunch of examples. Is that clear?
So I have a question about this mutual information training.
Yes.
So without experiment, what do you expect the representation will contain? I mean, what kind of information will the representation contains if you train with mutual information?
I'm not sure I understand the question.
What information will your representation contain if you do the mutual information training? Yes.
Right. Well, so we can only answer this question empirically, right? So for example, what we've done in this case is we've taken data sets like these data sets like Tiny ImageNet and CFAR 100 and so on, and they have labels, and we can check whether among the features that it has detected, you have good predictors of those labels. But it's hard unless you know what you're looking for to check whether those representations capture those factors. There's no general way to say, oh, it's going to capture prosody. Well, I think the only way to answer that question is to use maybe a small data set for which you know the prosody and then see whether the representations predicts it.
Thanks.
Okay. So I have one more question about the gap between the fast thinking and slow thinking you were showing.
Yes.
So I'm just interested when we think about the fast thinking as a, let's say, an emergent phenomenon on the really trivial units, which is the way how it works, let's say, even for the neural networks in our brain.
Yes.
What needs to be changed for the slow thinking? Do we need more complex units, maybe agents, or do we have to change something else?
So I don't think it's a matter of changing the units. It's a matter of changing the style of computation. But really, we don't know the answer to this question. Like, what kind of neural net architecture will be able to capture the style of sequential, conscious, system to slow tasks. One of the directions that I've been investigating is, well, So first, you need some sort of recurrence, because what happens with the fast computation is similar to what happens in the feed-forward net, where you just get the answer in half a second. For the conscious processing, it's probably more something dynamic, involving convergence of the system to answers and going through steps. And these steps might even be communicable, so with conscious processing. And one of the things that I think is very promising in this direction is to use attention mechanisms in order to focus the computation in these system 2 style on a few elements of the representation at a time. So if you think about your own consciousness, in other words, consciousness here as what you're attending to in your mind at any particular moment, well, even the word attending to says that you're focusing. You're focusing on a few elements that you're conscious of at one particular time step, and then half a second later it's going to be a different thing, and then half a second later it's going to be a different thing. So right now we don't have neural net architectures which do that, but we have the building blocks for this using attention mechanisms.
So the students, for the people at our workshop, the students, if you have any questions, you're welcome to ask. So we still have BENGIO for another 10 minutes. So
there is one question by Santiago. Maybe after I will encourage students to ask YOSHUA questions, not just strictly related to the presentation, but also more general questions about career or whatever you want.
Yeah. So, hi. The talk is very interesting, especially because this topic is like very emerging, but now and then, like representation learning, unsupervised learning. But there's a typical thing which is relating all these techniques with neural nets and architectures and you know, the implementation per se. So I think some things are taken for granted, especially if we had like previous architectures like autoencoders that did unsupervised learning, where we knew that we had to compress things in the latent space and then recover back the same representation in the input, but we had to enforce the bottleneck such that there was not a copy-paste function.
Right.
So nowadays, with all the new emergence of self-supervision, which is like different tasks than just reconstructing, it's relating pieces of data, how necessary is to compress that space? Can we like put a mixture of self-supervision tasks and expand our space from the input signal to a higher dimensionality, and we could take advantage of that?
Right, so actually we don't need to compress that space. The old style autoencoders required this, as you said, because otherwise you would potentially just learn the identity, right, and learn nothing interesting. But once you start putting, in a way, additional pressures on the representations, for example, the denoising autoencoders, just one little modification prevents this collapse. And you can train denoising autoencoders with, you know, a larger representation than the input. I mean, in general, it's not necessarily useful, but you can do it. In typical realms like images and sounds, the input is very high dimensional, so we tend to want to reduce dimensionality anyways. But the denoising architecture is actually a special case of self-supervision, right? So what we're doing, let's say the noise consists of hiding some of the inputs, and then the reconstruction tries to reconstruct everything, including the missing ones. So that's actually a self-supervised learning method. And those kinds of self-supervised learning method, they will not care how big is your representation. I mean, of course, they will care in the sense that you could overfit and things like that, but they will not collapse to something weird because you have more dimensions in your code than in the input image.
Questions?
Thank you for the talk. I really enjoyed that. Actually, in May 2017 in Montreal, you mentioned about the consciousness per year.
Yes, yes.
And actually, the idea is about to have a kind of symbol RNN, you know, to provide some latent variables. On top of that, we need to have a kind of consciousness RNN in order to actually focus on some latent variables, and the input has some. The input is the hidden latent variables and also the noise. And could you please provide some hints about how we can actually implement this actually the consciousness RNN and also the verifier network, you know, in order to verify what the conscious state learns, you know.
Right.
And what the good data set that we can collect for in terms of the speech processing for this kind of task, you know.
Well,
thank you.
So the idea, let me just recap a little bit for the audience what the conscious prior idea is. So it's related to learning representations, and it's related to the earlier questions about system 2 processing, conscious processing, and the use of attention to select just relevant things at each time step. The problem with this that we faced is that if you only select a few dimensions at each time step for this high-level recurrent net, how do you make sure that you don't have a collapse of the representation to uninteresting things that are easy to predict, right? So if it's similar to the problem where I was talking about when I talked about the mutual information between regions, between representations of patches, like here, say. Right. So to implement the consciousness prior, we have this issue that if we're trying, say, to predict this from this, like a future high-level selected aspect from a previous high-level selected aspect, like my next conscious thought from my previous conscious thought. If I just use something like maximum likelihood in the objective, then I can, get to absurd answers, and the encoder, which maps the low-level data to the high-level representation, might learn something stupid, like a constant. And in fact, this is exactly the reason why we worked on mutual information. So the motivation was to be able to implement something like the consciousness prior. And so I think now we're starting to have the tools to implement things of that type, and I have a couple of students who are working on these questions. So it's still science is a very slow process, and you have to be patient and look at the obstacles and, knock them down one after the other.
Maybe we have time for one or two quick questions. Students?
Just on your last point, what is the state of machine learning from a scientific point of view and an industry point of view, or engineering point of view?
Right.
Let's say engineering, since we're here.
Yes.
Because those are two aspects that kind of go in parallel ways in a certain sense.
Right. Okay, so I could speak for a while on these questions, but let me try to go for brief answers. So on the scientific point, it's kind of funny because we've made fairly amazing progress in the last few years, and deep learning and machine learning have been deployed in industry and have been allowing to really make huge advances in things like speech processing and computer vision and natural language processing. But at the same time, we are very far from human level intelligence and human level competence in many of these tasks. So, I've talked about many of the limitations in other talks, and this is, of course, what researchers are trying to do, like looking forward and like what's missing. Now, to go back to and maybe it's going to take decades or hundreds of years to really fill that gap. We don't know. But the good news is, even though we're far from human level AI, the science that we have achieved up to now has a huge further potential in industry, in all kinds of sectors. In fact, pretty much all of the sectors of industry. And a lot of companies have understood that. And they've understood, so why is it that I'm saying this? So you could say, well, okay, we've already achieved things, and now, is there anything more to do from an engineering point of view and from the point of view of deploying these ideas in products and so on? And the answer is yes. And the reason is we're just scratching the surface with the techniques we currently have in terms of how they can be applied. There are many ways you can improve, or you can even apply these things in completely new sectors of society. I mean, whole new areas like applications in the healthcare, or applications in the environment, or applications in legal system, or applications in education. People are just barely starting to scratch the surface of these applications. And what's interesting is not only there are areas we haven't started exploring, how we could apply these things, but even in areas where we already started, simply because we can do better engineering, we can train on more data, we can collect more data, and we know that the larger the data set, the better the result is going to be. So simply by doing, a better job at collecting data and collecting more of it, we can improve. Companies are building chips specialized to this kind of computation, and it's bringing improvements in energy consumption, price, computational speed that are orders of magnitude better than what we currently have. So in the next 3 to 5 to 10 years, we'll see a rapid progression in terms of the hardware. And this will further open the door to applications we're not considering because maybe it would be too expensive, or, yeah, all of these things together means there's like a huge potential of engineering work on the deployment and design of new solutions based on machine learning.
Maybe the very last question. Okay, maybe the last question could be, here there are many young students, and what do you suggest to study? What do you think is promising? Some promising research direction you mentioned, but what are the others that you think we should focus in the near future?
Well, there are many paths that are open in front of young people who are interested in machine learning. So I can't say that there's like one direction, but clearly, compared to other areas of computer science, machine learning is a bit more mathy, right? So even if you're going to be doing engineering and applying those techniques, it's good to be able to read the papers that people are writing in this field, and there's a lot of math there. Right, so one advice is, make sure you study well your math, or go back to it. So for example, in the deep learning book that I co-authored, the first third of the book is really about recap of mathematical and computer science notions that are relevant, and we're pointing to a lot of text which could be good background. So that's one advice. The other advice is get your hands dirty. Okay, so the math is nice. But if you understand the math, but you don't build the intuitions, it's not going to work. And how do you build intuitions? By doing things, by doing experiments, by trying it out and failing and trying again, and until you make these things work, and ask around, help if needed, read. So I see, for example, students coming from some countries have a lot of hands-on experience. They like in their undergrad, they've done 10 different projects using machine learning. And it's just undergrad. Whereas like in other countries, say like France, you don't find that. It's kind of, what are they doing? Like they're just doing math. They don't do any like real stuff. So no, but seriously, even if you want to do,
that's Europe.
Even if you want to do research, like very mathy research in machine learning, you want to get your hands dirty, because this is how you build the intuitions, and it's with the intuitions that you know what theorems you want to prove. So in any case, I think you need to do both the effort to try to understand the underlying math, which isn't that complicated, but it's more than the standard fare of computer science. And you need to do a lot of hands-on, practical, experimental work to understand these algorithms, program them yourself, not just use the libraries, but like try to actually understand what's going on inside under the hood.
Thank you very much.